In 2023, attackers completely hijacked user accounts at Booking.com. And they did not crack passwords, they didn't breach any databases.
Right, they exploited a single wildcard symbol in an OAuth redirect URL.
Exactly, a single symbol. Today's deep dive evaluates the mandatory architectural shifts required to secure production APIs. We are evaluating the transition from the historically vulnerable OAuth 2.0 framework to the strict, hardened mandates of RFC 9700 and the upcoming OAuth 2.1 specification.
Because the operational freedom of legacy OAuth 2.0 led directly to severe real-world exploits. I mean, beyond Booking.com, we saw the catastrophic Microsoft Azure AD vulnerability, CVE 2020-26870.
Which is massive.
Right. These incidents prove that discretionary security controls fail at scale. When developers are given the option to configure security parameters loosely for the sake of convenience, catastrophic vulnerabilities inevitably follow.
And our sources today include the official RFC 9700 documentation, identity provider deployment specifications, and, of course, verified vulnerability reports. We will equip you with the exact architectural shifts required to migrate your delegated authorization infrastructure into a modern, hardened posture.
Let's get into it.
Part 1. Framework section. We must define the core terminology before analyzing the architecture, because implementers frequently conflate OAuth and OpenE Connect.
They do, constantly.
Right. OAuth is strictly a framework for delegated authorization. It grants a client application access rights to perform operations on a resource server. It does not authenticate the user.
OpenID Connect, or OIDC, is the authentication layer built directly on top of the OAuth framework. OIDC utilizes JSON Web Tokens, specifically ID tokens, to assert user identity, email addresses, and authentication timestamps.
So it's about the who.
Exactly. If you need to know who the user is, you implement OIDC. If you need to grant a system access to data, you implement OAuth.
The mental model for authorization requires a complete shift here. Legacy O 2.0 prioritized extreme flexibility. It accommodated a fragmented landscape of clients by leaving critical security parameters, like exact URL validation and token transmission constraints, as optional choices for the developer.
Which was a disaster waiting to happen.
Right. And the modern paradigm, established by RFC 9700 and OAuth 2.1, enforces strict, mandatory, secure-by-default safeguards. Discretion is removed entirely. But wait, I have a question about that.
Go ahead.
If the operational flexibility of OAuth 2.0 pushed the security burden onto implementers, why did the industry tolerate it for over a decade instead of enforcing rigid constraints from the start?
Well, the initial framework design had to accommodate an entirely fragmented technical landscape. Over 10 years ago, web, mobile, and enterprise clients lacked standardized cryptographic capabilities.
Oh, right. The environment was completely different.
Exactly. Browsers handled cross-origin requests inconsistently, and mobile operating systems lacked secure enclave standards. The framework had to be malleable to function at all.
I see.
Today, standardized cryptographic APIs exist globally across all modern environments. Because the baseline technology has matured, the framework can deprecate those legacy modes and strictly enforce hardened postures.
Makes total sense. Moving on to part 2, technical deep dive. We will examine 3 specific vulnerability vectors and their mandated defenses, starting with the failure of URL routing.
This is a big one.
Subsection 2.1. Open redirects and precise verification. So authorization servers use a callback URI to redirect the user agent back to the client after authentication. This redirect acts as a fundamental bridge.
And attackers target this bridge by manipulating query parameters to route tokens directly to hostile infrastructure.
How does that actually happen during the request?
During the authorization request, the client transmits a query parameter containing the target callback URI. If the authorization server uses loose pattern matching, permits direct retraversal, or accepts arbitrary subdomains, attackers weaponize this trust.
Which brings us back to Booking.com.
Right. The Booking.com exploit leveraged loose wildcard matching on registered callback endpoints.
Yeah.
An attacker registers a malicious domain, like attacker-booking.com.
Oh, wow.
Yeah, and if the server's validation logic simply checks if the string booking.com exists anywhere in the URL, it approves the redirect.
So they just append it to their own domain.
Exactly. Attackers crafted phishing links targeting the legitimate provider, but manipulated the callback to point to their own domains, achieving full account takeovers. CDE 2020-26878 exposed a similar direct redirect manipulation flaw within Microsoft Azure Active Directory.
That is terrifying.
The table on screen compares the catastrophic failure rate of loose pattern matching against bit-for-bit exact string matching. The defense implementation is absolute. Servers must enforce bit-for-bit exact string matching against pre-registered whitelists.
Meaning zero flexibility.
None. Wildcards, subdomains, and partial paths are strictly prohibited. Every environment, from local development to staging and production, requires a separate, fully qualified domain registration.
Are there literally no exceptions to this rule?
There is only one. The sole exception is for native applications requesting random loopback ports, specifically 127.0.1, to avoid port collision during local execution.
Okay, but the requirement for exact string matching sounds straightforward, but enterprise environments deploy hundreds of microservices. Managing a static exact match whitelist for every single development, staging, and production environment introduces massive operational overhead.
It does.
Why did the specification remove the flexibility of secure pattern matching?
Because secure pattern matching at scale is a myth.
Really? A myth?
Absolutely. Regular expression parsers differ across programming languages. A Regex pattern that securely validates a subdomain in a Node.js gateway might contain a bypass vulnerability when evaluated by a Java-based identity provider.
Oh, I hadn't thought about cross-language Regex discrepancies.
Right. Bit-for-bit, exact string matching eliminates the parsing engine entirely. It relies on a simple cryptographic hash comparison or binary string equivalence. The operational overhead of registering hundreds of exact URIs is the necessary price for mathematical certainty.
That is a harsh reality for DevOps teams. Let's move to subsection 2.2, state integrity and code interception. Securing the destination URL is only the first step.
Right, because if the destination is correct, an attacker shifts their focus to intercepting the payload while it is in transit.
Exactly. Legacy implicit grant flows delivered access tokens directly inside the URL fragment. This exposed tokens to HTTP refer headers, embedded analytics scripts, and server access logs.
It was a nightmare for logging visibility.
Yes. CVE 2021-26708 demonstrated how misconfigured social logins leaked authorization codes directly into accessible client-side logs. So how do we defend against this?
To neutralize interception in transit, the framework mandates proof key for code exchange, or PKCE, defined in RFC 7636.
Okay, break down PKCE for us.
Think of PKCE as a cryptographic code check. The client drops off a code and generates a unique hashed claim ticket. Even if an attacker steals the ticket on the way back, they cannot retrieve the code because they do not possess the original cryptographic stub that matches the hash.
That's a great way to visualize it. Technically, how does that handshake execute?
Technically, PKCE initiates a cryptographic handshake. The client application generates a random, high-entropy secret called the code verifier at the start of the flow. It sends only a SHA-256 cryptographic hash of this secret, called the code challenge, to the authorization server.
So the server only sees the hash.
Right, the server stores this hash. When redeeming the authorization code at the token endpoint, the client must present the original plaintext verifier. The server hashes the plaintext verifier and compares it to the stored challenge.
Which means interception is useless.
Exactly. If an attacker intercepts the authorization code on the network, they cannot exchange it for a token because they cannot reverse the SHA-256 hash to produce the plaintext verifier.
Wait, I need to clarify a redundancy in the specifications.
Sure.
If PKCE completely secures the code exchange cryptographically through this hashing mechanism, why does RFC 9700 still mandate the inclusion of the state parameter?
That is a very common question. PKCE neutralizes token interception by ensuring the party that requested the code is the only party that can redeem it. It protects the code from being stolen.
Okay.
The state parameter solves an entirely different vulnerability, which is login cross-site request forgery, or CSRF.
Walk us through a login CSRF attack.
In a login CSRF attack, an adversary starts an authorization sequence using their own identity provider account. They capture the callback link containing the valid authorization code before their browser consumes it.
So they have a live, unredeemed link.
Yes. They then trick a logged-in victim into clicking that specific link. The victim's application consumes the attacker's code, binding the victim's local session to the attacker's OAuth account.
Oh, wow. So the victim is now logged into the attacker's account without realizing it.
Exactly. If the victim enters a credit card or uploads sensitive files, they are saving them directly to the attacker's account.
And the state parameter blocks this.
It prevents this forced session binding. It is a unique, unguessable nonce bound to an HTTP-only same-site cookie on the client's machine. When the callback returns, the application verifies that the state in the URL matches the state in the local cookie.
Which fails for the victim.
Right. If the attacker sends their link to the victim, the state values will mismatch and the transaction is aborted. Both PKCE and state are mandatory.
Excellent breakdown. Let's move to subsection 2.3, client-side token storage paradigms. Once the authorization code is securely exchanged and the client receives the tokens, the architecture faces an immediate physical security problem.
Where does the browser actually store them?
Yes, storing tokens directly in the browser introduces immediate trade-offs. Storing tokens in local storage provides JavaScript with full access to the credentials.
Which is incredibly dangerous.
It exposes the tokens directly to any cross-site scripting or XSS vulnerability present on the domain. Malicious scripts can read the storage objects using a simple window.localstorage.getItem command and exfiltrate bearer tokens to a remote server.
Right, and the alternative, placing tokens in HTTP-only cookies, mitigates XSS exposure because the browser prevents JavaScript from accessing the cookie layer entirely.
But cookies have their own issues.
They do. Cookies are automatically attached by the browser to every request sent to that domain. This introduces classic CSRF vulnerabilities if session integrity and same-site attributes are not strictly enforced.
As shown in the storage diagram on screen, the hybrid model physically separates the long-lived and short-lived credentials. Modern defense models require this hybrid execution architecture.
Yes. Long-lived refresh tokens must be strictly confined to HTTP-only cookies with the same-site strict flag. This shields them entirely from JavaScript execution and XSS exfiltration.
And the access tokens?
Short-lived access tokens must reside exclusively in volatile JavaScript memory. They are never written to local storage, session storage, or IndexedDB.
Let me clarify the memory aspect. When you specify volatile JavaScript memory, you mean the token is stored in a standard variable, like a React state object or a JavaScript closure. The credential evaporates the exact moment the user closes the browser tab or refreshes the page because it never touches the actual hard drive.
Correct. By keeping access tokens in volatile memory, the architecture prevents physical disk persistence. It limits the credential's lifespan to the active browser session.
So what happens on a page reload?
When the page reloads, the front end simply makes a silent request to the backend. The browser automatically attaches the HTTP-only refresh token cookie, and the backend issues a new access token back into volatile memory.
Part 3. Practical application. Translating these specifications into production systems introduces significant friction. We will analyze 3 operational realities, starting with Scenario 1.
Single-page applications and third-party cookies.
Yes. SPAs historically relied on invisible background iframes to refresh tokens without forcing the user to re-authenticate. The global deprecation of third-party cookies by major browsers breaks this traditional SPA token refresh flow entirely.
Browsers now view an authorization server's cookies as a cross-site tracking mechanism when the server operates on a different domain than the front-end application.
Which is almost always the case in modern architectures.
Right. Safari's intelligent tracking prevention and Chrome's cookie phaseout actively refuse to transmit these cookies within an embedded iframe. SPAs must use full-page redirects or top-level interactive pop-ups to capture the authorization code at the top-level frame, where cookies are treated as first-party context.
Engineers face specific issues here, particularly with cross-domain partition cookies causing state mismatch failures. GitHub issue #5871 for the BetterAuth library highlights this exact failure.
I remember that issue.
When an identity library utilizes partition cookies, often referred to as chip-PS or cookies, having independent partition state for the state parameter, the cookie locks exclusively to the backend domain's partition. When the front-end attempts to handle the callback redirection, the expected state cookie is missing from the front-end's partition. The validation fails.
So what is the mandatory fix?
The solution requires issuing short-lived 24-hour refresh tokens to minimize login friction while strictly managing state continuity across domains via backend for front-end proxy patterns.
Perfect. Let's look at Scenario 2. Secure redirection in native mobile environments. Native applications face a unique cryptographic constraint. They cannot hold static client secrets because compiled mobile binaries are easily reverse-engineered.
So they can't authenticate securely like a backend server.
Exactly. Historically, mobile developers use custom operating system URL schemes, like myapp.callback, to receive authorization codes.
Which is basically broadcasting the callback to the whole device.
Right. This architecture is vulnerable to rogue app hijacking, where a malicious application registers the exact same custom scheme on the device to intercept the authorization code.
And the modern solution?
The solution is a mandatory migration to verified deep links. This means utilizing Apple Universal Links on iOS and Android app links on Google platforms.
Meaning they drop the custom schemes entirely?
Yes. These mechanisms abandon custom schemes and use standard HTTPS URLs. They require the domain owner to publish a cryptographic verification file, such as the Apple AppSite Association file, directly on their web server.
So the OS verifies the domain ownership.
Exactly. This file maps the domain to the application's unique cryptographic team identifier. The mobile operating system securely fetches and verifies this file before routing the callback.
Wow.
This guarantees that only the authorized cryptographically signed application receives the authorization code from the operating system.
Scenario 3 examines provider ecosystem variations. The flexible nature of legacy OAuth allowed major providers to develop divergent architectural strategies that engineers must accommodate.
Let's start with Google.
Google operates a consumer-first philosophy. Google mandates highly granular read and write scopes and explicit application verification workflows. To maintain continuous background processing without user presence, developers must request the offline access scope to generate refresh tokens.
And if you need to force a login,
Passing the prompt consent parameter commands the Google server to bypass any existing single sign-on session and force explicit reauthentication.
Microsoft, on the other hand, utilizes an enterprise-first paradigm. It relies heavily on tenant-wide admin consent. This streamlines deployment for internal corporate tools, but creates concentrated risk profiles.
Right, like the Storm 1286 exploit.
Exactly. The Storm 1286 exploit specifically targeted Microsoft 365 environments by utilizing these broad admin-consented permissions. An attacker compromises a single administrator, approves a malicious application with tenant-wide read-write permissions, and utilizes that OAuth application for invisible lateral movement across the entire organization's email and SharePoint infrastructure.
A single point of failure.
Exactly. Now, GitHub approaches the problem differently. GitHub separates automation privileges from human user session turnover by utilizing GitHub apps.
Because tying access to a human developer breaks the CI/CD pipeline if that developer leaves the company.
Precisely. Instead of using a human's OAuth token, GitHub apps use installation tokens. This ensures uninterrupted bot execution and applies the principle of least privilege regardless of personnel changes.
Implementing these varying architectures requires strict debugging protocols. Engineers must trace authentication flows using the browser DevTools Network tab. You must enable the preserve log setting.
That is critical.
Without preserve log enabled, the rapid sequence of HTTP 302 cross-origin redirects will immediately clear the request history, destroying your debugging visibility. You must inspect the query strings, redirect URIs, and dynamic state values on every single hop.
And you need to watch for two standard error codes that dictate your debugging path. The invalid error code indicates that the authorization code or the refresh token is expired, revoked, or has already been used.
Because authorization codes are single use only.
Right. The specification mandates that. If a code is replayed, the server must revoke all tokens previously issued based on that code. The second error, unauthorized client, indicates that the client application is attempting to use a grant type it is not registered to use on the authorization server.
Which brings up the complexity of logout. It is a major failure point in these architectures. Deleting a token locally from the client application's volatile memory or clearing the local cookie does not revoke the token at the API gateway or the identity provider.
No, it doesn't.
The application must explicitly call a global revocation API endpoint to destroy the database records.
And revocation becomes a severe architectural bottleneck when utilizing self-contained JSON web tokens. Because resource servers evaluate the cryptographic signature of a JWT locally to reduce latency, they do not poll the identity provider on every request.
So they have no idea if the token was revoked centrally.
Correct. Therefore, revoking a JWT before its natural expiration is practically impossible without introducing extreme overhead. It requires implementing complex, real-time edge blacklists in memory stores like Redis or adopting phantom token exchange patterns.
What is a phantom token pattern?
In a phantom token pattern, the front end receives an opaque, meaningless string, and the API gateway exchanges it for the actual JWT before routing to internal microservices.
That sounds complicated to implement.
It is. Most organizations fail to implement either correctly, leaving active JWTs valid even after the user clicks logout.
That brings us to our closing action items. You have 3 concrete tasks to execute this week. 1. Audit your callback URI logic in your authorization servers. You must enforce bit-for-bit exact string matching and remove all wildcards or partial path matching logic.
Non-negotiable.
2. Refactor your front-end application state. Purge all access tokens from local storage. Move your architecture to the volatile memory and HTTP-only cookie hybrid model we detailed today. 3. Eliminate legacy implicit grant flows entirely. Enforce PKCE validation on all clients, including both public SPAs and confidential backend clients.
You can find the mandatory specifications in the RFC 9700 documentation. We also recommend reviewing the OWASP HTML5 security cheat sheet for secure storage guidelines. Use JWT.io and OAuth playgrounds for active debugging and token payload inspection.
Drop your specific infrastructure challenges in the comments below. We are particularly interested in how your engineering teams are handling cross-domain partitioned cookie synchronization in your SPA architectures following the deprecation of third-party iframes.
And consider this final architectural challenge as you review your systems. If stateless JWT access tokens cannot be reliably revoked before their expiration window lapses, and refresh tokens are tightly bound to a specific device, how must an enterprise zero-trust architecture handle instantaneous real-time session invalidation when a device is compromised mid-session?